Hello, welcome to AWS's virtual reInvent. My name is David Murray and I'm a principal solution architect at AWS. This session is Con 204. I've been with Amazon for about 6 years. I've been to many reInvents and I think this reInvent is a first for a lot of things, especially for me. It's certainly a first where I've had no cracked lips, thanks to the Vegas aircon. It's one where I haven't done my 10,000 steps every day. And probably the best one is it's the first presentation at reInvent I've given where I've allowed to have my dogs, George and Ringo, here watching. Now, I spend my day at AWS working close with one customer. It's awesome that I get to work. My only customer is Snap. Snap really operate kind of on the bleeding edge of technology. They push our boundaries, they push technology boundaries, and they push limits. I get to learn from them every day. I get to see and work with technologies that I wouldn't get elsewhere. So it's been a really great journey for me. And this session today is to talk around Snap's evolution of their compute platform. I'm joined by Aaron Sheldon, who's a software engineer at Snap. And Aaron has really pioneered Snap's journey into the Graviton and ARM space. Aaron's going to share his story around how Snap have kind of evolved their compute platform from a Kubernetes-based service mesh running solely x86 to implement some of the ARM-based instances at AWS like the Graviton 2. Now, for the agenda today, a couple of things we want to make sure that we cover today is the first is I'm going to go through the evolution of Graviton. So where we start with Graviton, why we started, and the evolution of some of the hardware we've kind of innovated at Amazon. Then I'm going to talk around some of the challenges or some of the implementations we've done with some of their services. And in particular, in this service, it's EKS, the Amazon Elastic Kubernetes service, and why that makes a lot of sense for running ARM-based instances and Graviton 2 and Kubernetes. Then I'm going to go past to Aaron for probably the most interesting part of the presentation. Aaron's going to share his journey around how Snap have integrated Graviton 2 into the service mesh. And the idea is, what we hope is that after this session, you guys are going to take away a lot of lessons that Snap have encountered on their journey, what the benefits they have, how they've benchmarked, some of the performance and some of the cost gains they've had to help you guys in your own journey towards introducing ARM-based or Graviton instances into your own workloads. So, starting from the beginning, so what is Graviton and why did we kind of invest in this space? I mean, as most people know, we have really in-depth partnerships with Intel and AMD. We have worked with them for a number of years. They have powered and innovated on our behalf for many of our EC2 instances. And that's always going to continue. We still have a very, very close relationship with Intel and AMD. But what we noticed was over the years of running cloud computing, we started to take lessons around how we at AWS see customers using cloud native workloads at hyperscale. We learned a lot about usage of compute at that scale. And we started to take some of those lessons, and when we worked with customers, they were seeing how we could take those lessons a little further and innovate on their behalf to look for performance and cost gains in the chips that we're using in some of the instances that we have. So you look at our journey. I mean, we began working with Annapurna Labs over 5-6 years ago. Now, Annapurna Labs is actually an Amazon company. And if you look at some of the innovations we've had in the hardware space, it started really with maybe at the I/O accelerator card. And you see that in a lot of the EC2 instances that you're using today for accelerating I/O2 or I/O workloads. And that moved into the Nitro card, and you see a lot of publicity around that. For us in AWS, this really revolutionized cloud computing from our perspective, because what it allowed us to do was to tackle a really tough goal. And the goal we set out was to make EC2 indistinguishable from bare metal. So how we done that with the Nitro card was we would be able to decouple and move the processing power from networking and storage and security and management and take it from the EC2 instance and put it into its own card, which is the Nitro card. That allows us then to run the entire compute power of the EC2 instance purely for running customer workloads. And that's really been at the heart of a lot of our innovation since that's been released. And then we moved into the CPU and we released what you'd seen in 2018 around the Graviton and Inferentia chips. And we've innovated not overnight, but over, as I mentioned, 5 or 6 years back from 2018 on how we got to today. So let's look at the first instance type. The chip you're seeing there is an actual real Graviton 1 chip. It is custom built by AWS and it's using the 64-bit ARM Neoverse core. Now, it was targeted for optimization and optimizing cloud native workloads. Now, when you peel back some of the covers and you look at some of the technology in this space and the technology of the Graviton 1 chip, I mean, it was hardly earth-breaking or groundbreaking back then. It was, if anyone is like me and a bit nerdy around CPU processing and how you measure the improvements in that, it was designed as 16 nanometers. Now, nanometers, to break it down a little further, is essentially the length of the transistor gate. In kind of easy terms, it's essentially the distance between the transistors and other CPU components. Now, the smaller you can make the nanometer size, the more transistors you can fit into an area of space. So with 7 or 16 nanometers on the Graviton 1 chip, we were able to make or introduce 5 billion transistors. Now, to give you some context around that space back in 2018, let's look at the Intel Broad Lake chip. So that had 14 nanometers and was released in 2014. But where the real innovation was with Graviton 1 was it made AWS the first major cloud provider to introduce ARM-based chips into their compute platform and make them available for customers. And that was really great. But the best part of that was it then let us work very, very closely with our customers. And with our customers, we could then understand their workloads on ARM, understand their use cases, understand their performance gains, and where they wanted to take their ARM journey. So within the space of a year, we were able to rapidly iterate on the chip we had released, which was Graviton 1. And that's when you've seen in 2019, we released the second generation of Graviton, Graviton 2. And again, that's another chip, it's the real Graviton 2 chip you're seeing in the presentation. And one thing, again, is it's custom built AWS silicon, and it's, again, 64-bit ARM and using the Neoverse N1 core. Now, we worked very closely with ARM during the innovation for that. I mean, they brought their expertise in the chip making, and we brought some of our expertise on running large-scale workloads in the cloud. And when you peel back the technology of Graviton 2 versus Graviton 1, you can see some of the massive improvements we have, even just in the hardware space. If you remember, I mentioned the nanometers, and we had 16 nanometers in Graviton 1. In 1 year, we were able to reduce that and introduce a new chip that was running at 7 nanometers. Now, in 2019, that is very much at the forefront of CPU chips and performance in the nanometer space when you take that as a measurement. And there's very few companies who are publicly running chips with smaller than 7 nanometers. And that allowed us to increase our transistors from 5 billion transistors to 30 billion. We also made some innovations in the cache. So we went to a large L1 64K cache for instruction. And then we had a large 1 meg L2 private cache. And that 1 meg was private to every vCPU. So think of that from your perspective. Every vCPU is attached to a physical core. And the physical core is dedicated to that vCPU. So that 1 meg of cache is now available solely to you to implement your workloads. So when you look at it from a performance perspective, you now have a large amount of cache that you can run your workload or a large percentage of your workload in that never now has to reach out to memory. So you don't have that performance hit of going to memory. And that's one of the areas we see real performance gains in Graviton 2. Now, the fact we don't have to do simultaneous multi-threading and we have a dedicated physical core to vCPU is also great from a security perspective. Because no longer are you sharing the core between other customers. It's dedicated directly for you, and you can be sure from a security perspective that you have full access just to that and nobody else does. So that was a real difference again between Graviton 2 and Graviton 1, and some of the benefits that customers were really starting to rave about and why they started to get really introduced and running Graviton 2 really quickly after we released it. Now, that brings us to the numbers and some of the performance gains that we got. Graviton 1 had 16 physical cores, and what we had in Graviton 2 was we were 4 times that. So with the 4 times amount of compute cores, we had 64. And we had 5 times the memory. And you add that to the cache performance I was talking a moment ago, we were seeing 7x performance versus Graviton A1 or EC2 A1, which is Graviton 1 instance types. So it was a massive gain, and it is a massive gain. And that's why we now have access to work with so many different workloads. When we started out with Graviton 1, it was the majority was scale out compute workloads. Now, as you've seen from my last slide, now we're targeting HPC, high performance compute, analytics, database, in-memory cache and in-memory database, container workloads. So it opens up the spectrum of workloads that customers can use on EC2 to a whole new variety. And that's why we're seeing rapid adoption of Graviton. Now, adoption of Graviton didn't just happen with our customers. We also seen rapid adoption of Graviton inside the AWS services that customers use. One that comes to mind was Elasticache. Elasticache were one of the first to introduce support for Graviton 2 in 2020. And what we're seeing is customers of Elasticache are seeing the same benefits of EC2 customers who are using Graviton. They're seeing performance gains and cost gains. But the service we want to talk to you about today is EKS, which is Elastic Kubernetes Service. As I mentioned previously, the introduction of ARM into the server world, it goes very much hand in hand, and it works very well with the introduction of containers. And specifically in this time, we're talking about Kubernetes. ARM scale-out workloads and Kubernetes scale-out workloads really work well together. And that's why we've seen EKS introduce support for Graviton 2 very early in 2020. And I want to just kind of break down some of the areas of support inside EKS that you should be aware of and know about, and some of the benefits you get. So one of the key things to remember is that it's end-to-end multi-architecture support. It's not just inside of EKS. And what that means to you guys as customers is we support it right through from the container registry. So the Amazon Container Registry, ECR, so it has full support as of 2020 for multi-architecture containers. So you can create your workloads, upload them to the ECR Container Registry, and an EKS can pull directly from ECR. EKS has specific tooling inside the product to actually help with support of multi-architecture containers. And that makes it a lot easier for customers like yourselves and Snap to introduce multi-architecture support and introduce ARM-based or Graviton instances into their workloads. And what we're seeing with that is customers can introduce them into production, or they can introduce them into test. You're going to hear exactly how Snap done that. And it's seamless from an EKS perspective. One of the reasons it makes it a lot easier from EKS is that we also have support for managed node groups. And managed node groups was a service that was a feature that was introduced last year. It took us from just managing the Kubernetes control plane right into managing the worker nodes inside the Kubernetes cluster. And the key part here for a Graviton perspective is our managed node group supports multi-architecture managed node groups. So we can manage worker node instances of both ARM, which are Graviton instances, or our x86 based instances that we always support. And that's really big as a benefit from customers. One thing to note is our support is for ARM version 8.2. And Graviton 2 is compatible with ARM version 8.2. So it's the Graviton 2 instances that we do support inside of EKS. So with that, what I'm going to do now is I'm going to hand it over to Aaron. And Aaron's going to share the journey for Graviton inside of Snap. And as I mentioned before, the lessons you learn from what Snap went through and some of the benchmarks and performance gains that they had, we're hoping that you guys will get a chance to take some of those lessons and take some of those instructions that Snap are able to provide and implement some of these workloads yourself inside of your own environments and start to test them to see that you're getting performance and cost gains. So with that, I'm going to pass it over to Aaron Sheldon from Snap. So thank you very much.
Thank you for that introduction to Graviton 2, David. My name is Aaron Sheldon. I am a software developer in Snapchat infrastructure, and I am happy to be sharing some of what we've been doing at Snap recently with Graviton 2. Snap is a camera company and creator of Snapchat, an app used by 249 million people per day on average. We reach more than 90% of the 13 to 24-year-old US population and 75% of the 13 to 34-year-old US population. Snapchat has spent the past 2 years migrating from a monolithic architecture to a service-oriented architecture. This reduced Snapchat's compute costs by 65% while improving reliability and reducing latency. This new architecture is powered largely by open source technologies. Our service-oriented architecture is built as a service mesh based on the Envoy proxy. We run a single service mesh over hundreds of Kubernetes clusters and multiple independent cloud regions, which is all controlled by our internal service mesh control plane technology, Switchboard. So what does a service mesh have to do with Graviton 2, and why did Snapchat choose to pursue Graviton 2? Now that Snapchat has migrated from a monolith to a service mesh, it is possible for services to migrate to Graviton 2 independently of other parts of the system. Teams who have done this on their services have substantially reduced Snapchat's compute costs. In the graph seen here, we can see the costs of a single Go-based service as it migrates from a C5 fleet, with its costs represented in blue, to a Graviton 2 C6G fleet represented in green. Initially, there is only C5 cost, then a fixed Graviton 2 fleet and variable C5 costs in a period with increasing load on this service. And finally, the C5 machines were shut down and all costs became variable Graviton 2 C6G costs. These cost reductions are from a combination of reduced fleet size from improved performance and lower pricing. All Snapchat workloads on the ARM64 architecture were, until recently, AMD 64 workloads, with no ARM64 specific optimization work done as part of this migration. So, Snapchat moved to multiple architectures. Snapchat runs its service mesh on top of Kubernetes, which in turn is relying on Docker to pull and run containerized applications. When Docker downloads a Snapchat-built Docker image, instead of downloading a Docker image, it downloads a Docker manifest list. This manifest list contains references to the actual Docker images we've built per CPU architecture, and Docker automatically downloads and runs the correct image for the local CPU architecture. What this means for Snapchat is that we're able to build our applications from multiple CPU architectures, publish them all under a single name in ECR, the Elastic Container Registry, and then at runtime, Kubernetes can schedule pods on ARM64 machines or AMD64 machines without worrying about what the CPU architecture actually is. This enables easy, smooth migration with clear side-by-side comparisons of application performance and behavior. Language selection for services can assist or impede migration. Services written in languages like Go that make cross-compilation simple or unnecessary, like Java, and where the service lacks compiled binary dependencies, are the easiest to migrate. Services that depend on closed-source third-party binaries are the most difficult to migrate. For each workload, we need to ensure that we are getting the performance we expect from a migration to Graviton 2. To achieve this, what we do is launch a few pods running the application on the new CPU architecture and use our service mesh to traffic split a very small percentage of traffic to these test pods. Once we have a baseline, we increase traffic to these pods gradually while monitoring until they receive the same amount of traffic per pod as the existing AMD64 pods. When the pods are running on Graviton 2 and taking the same amount of traffic with equal or lower CPU utilization and equal or lower latency than our existing fleet handling identical traffic, we become confident enough to move forward with full migration to Graviton 2 on the service. It's important to make these decisions based on actual data. So, Snapchat learned a few things in this migration process. The first thing that Snapchat found is that there are big wins available on some of our largest workloads, which impacts cost in a meaningful way. On the other hand, not all our workloads have improved performance. Testing is important. Some of our workloads run more slowly on Graviton 2 than on our existing fleets. Predicting which applications will have improved performance is difficult, but testing which applications benefit and which do not is pretty straightforward on Kubernetes. With Kubernetes, you can operate at runtime as though an entirely different CPU architecture is just a different speed CPU. Then you can measure and decide to migrate or not based on a cost-benefit analysis. We also encountered and overcame challenges with the Kubernetes ecosystem. In particular, several upstream Kubernetes add-ons have no ARM64 compatible versions, or do, but don't take advantage of Docker manifest lists. Because of this, we build and self-host our own versions of several common Kubernetes add-ons. Though the Kubernetes ARM64 ecosystem is improving, it isn't at parity with the x86 ecosystem yet. Another thing is that Graviton 2 only fleets are better than heterogeneous fleets for any single service. Though Kubernetes and Docker can make CPU architecture seem like it doesn't matter, performance differences still matter. For example, consider a service that runs 10% cooler on Graviton 2 than on AMD 64, and that is configured to scale horizontally when the average CPU utilization of the fleet reaches 60%. In this scenario, the AMD 64 machines in this heterogeneous fleet might be running at 66% CPU utilization, while the Graviton 2 machines and the fleet average are only at about 60% CPU utilization. it is possible to reduce the scaling threshold to 55% CPU utilization from 60% CPU utilization to keep the AMD 64 machines from running too hot. But it would be better if the fleet were homogeneous to maximize the cost improvement that can be attained from Graviton 2. A second challenge with heterogeneous fleets on Kubernetes is that during scale down, the Kubernetes schedule does not know to prefer shutting down pods on more expensive or less performant hardware first. This makes operations more difficult and is another reason to prefer a homogeneous fleet to maximize cost savings and simplify operations. Finally, coordinating with AWS is a good idea whenever pursuing a large-scale migration. Working with AWS directly before doing large migrations means they can help avoid problems before they happen. We have found that Graviton 2 makes sense for our business, so Snapchat is looking to migrate more workloads to Graviton 2 in more regions and, for new applications, to use Graviton 2 as the default going forward. Please check out our engineering blog. It is at https://eng.snap.com/blog. Thank you very much.